All right. So what I want to do is I want to give you these. And Austin, you're going to be giving me you can do the chat thing where you tell me your answer. Okay, since you're going to be playing along there from home.
Yeah, I can do that.
So you can do a chat thing with
type in
me.
like A, B, C, D.
Yeah, A, B, C, D. Yep.
All right. Yep, I can do that.
And I can do chat here. Okay. And then the other three of you, you need your Chromebook out so you can see the questions. And then when you have the answer, you're going to put the A, B, C, or D on the front of your Chromebook so I can see that you have your answer figured out. And then that's your answer for whatever question we're on. Okay? And then I'll judge you based on your answer and make you feel really bad if you got it wrong. Just kidding.
As I know from yesterday.
Hold on, Austin. I gotta turn you up so I can hear you. Okay, what'd you say?
I said, as I know from yesterday, about making me feel bad over an answer.
Where did we leave off yesterday, Austin? Was it 19?
No, we got up to 15, unless there were
Okay.
more in a video after. But in class, we only got up to 15.
Okay. So I need to start on 16?
Yep.
Okay. So 16 asks, come on. There we go. At which point on the titration curve is A closest to twice that of HA? So we need to try to figure that guy out.
Yeah. Are we looking at the graph above 14?
Yep. So A minus is closest to twice that of HA. So if we remember correctly, we have HA plus we are titrating in hydroxide, yes, OH minus. That is going to make H2O plus A minus. Okay, so this H is going to come off. It's going to grab onto this guy, make this guy, and leave this guy behind. So where would this guy be 2 times that of this guy? Okay, well, up here, how much of this would we have left? At U, how much HA would we have left?
Not a lot.
Not a lot. And down here, we know that at this point, HA is going to be greater than this. At S, what's true of these two things? They're equal to each other, okay? So the only place where this still exists on this graph at these points, where this still exists and this is greater than this, has to be what? T, right? Good job, Emma and David. You need to put your sign on that side of your Chromebook so I can see it, because Emma makes a better door than a window. Love you, Emma. All right, let's try 17, see if we can figure out 17 here. Austin got it right. Good job. See if Eric's going to be brave enough to put his answer up this time. Calling him out. This one requires a tad bit of math. at the equivalence point, we would have this guy, the moles of this guy would be equal, you know, this guy would have been equal to this guy, right? The amount of this, oops, this is OH, I'm sorry, OH minus. There we go, sorry. Let's try it again. So we would have used up as much of this. So all of this would be used up and equal to this amount here. Okay. So if that was our amount, and we know that we had that many moles of that, the moles times the 0.04 for the molarity is going to give us 0.040. So this is the molarity here of our OH minus. This is how many moles of the OH, or liters of the OH minus that we use. So this is going to tell us the moles of OH minus. The moles of OH minus will equal the moles of HA at that equivalence point. Okay? And we know that we used how many liters? How many liters of HA did we use? They told us up here.
0.05.
Yep, 0.05, because they told us 50 mils right here. See that? Okay, so 0.05 liters. Okay, now you're having to do mental math here, right? What am I doing wrong? Yeah, 0.05, yeah. No, but this was Why did I do a 4 there? $50 divided by 4. Why do I have 50 divided by 4? This is what I've got.
Because you didn't convert it to liters.
Did I not multiply this right? Oh. I didn't multiply this out right. That's why. There should be another O in there. There we go. That's my problem. My mental math is bad. Right? Is that right? 0.1 times 0.04. Now this is where I go back and double check my math on here. 0.1 times 0.04. Yep, 0.004. Okay. Now, my problem is that my brain doesn't work well with this mess, with all these 0.00s and all that stuff. Okay. So when I go to do this, I move my decimal point over 4 places or 3 places here, and I move it 3 places here to do the math. Does that make sense when I'm doing my mental math? Okay. Because this divided by this is the same as this divided by this. Is that correct? You get the same answer. But my brain seems to work better with this guy for some reason. So when I do that, that's going to be 50 divided by 4, O. Okay. Now, I don't need to go much further than that. I can tell here right away. No, not 4O, just 4. There. I can tell right away that it's not going to be these two. Okay? Does that make sense? So I can get rid of those. So it's going to be one of these 2 things here. Now I got to reason this thing out now. Okay? So we're carrying this out. The indicator changes slightly past the equivalence point, which means that it's going to give me a calculated value that's just a little bit more than this, because it's going to be just past the equivalence point, which means I'm going to have a little bit more added in than I should have. So that's why I would pick B. But do you see how I can rule out C and D right away by doing this mess? You good? Okay. All right. Now we are on to, yes, Austin. Very good. B. Did you have B?
Yeah.
Good. C. Good job. All right. All right. So now we are on to 18 here. See if you can get 18. Kind of fun playing at home, isn't it, Austin? We are 0 for 4 right now. The correct answer is D. Your kinetic energy is directly related to your temperature. Since your temperature is the same, the kinetic energy will be the same for these. The energy will be the same. Now, the velocity of some of these particles is going to be different. Okay. This guy will be going slower than this guy, but the kinetic energy itself is going to be the same. Okay. Wah, wah, wah. All right, next one, density. The density of the gas in grams per liter is, which one of these will be greatest, or will they all be the same? Austin, do you have an answer for 19 yet? Okay, so he says C, and I've got 2 C's and a B. And David, why did you pick B?
Well, I just saw that the pressure for it was times 4, so I just divided up by 2 and times the mole mass by 2 to see that would be greater than the 58 for the mole mass.
Okay. So yes, the pressure is higher here than these two. So because this pressure is higher, the density is going to be higher. Good job. Pressure of each gas is increased at a constant temperature until the condensation occurs. Which gas will condense at the lowest pressure? David is correct once again. This has the highest IMFs. It's going to have because it has the highest number of electrons here. So this is more polarizable. So because of that, it will condense at a lower pressure. Okay, it's heavier. The IMFs are stronger. It's going to glob onto another particle of this and condense faster. All right, try 21. Austin, you got an answer for me?
No, one sec. Almost. Still reading.
Well, I'm going to play a little song for you because this comes up a lot in these AP questions.
One of these things is not like the others. One of these things doesn't belong. Can you tell which thing is not like the other by the time I finish this song?
And he's done. So which is it? Which thing is not like the other? Let's see. That would be A. A. Very good. Everybody got that one right. Excellent. Okay. So the mass percent here, right. The rest of these have carbon in them. So that's not going to throw this off. This guy is, though. Okay. So quite often you're looking for the thing, the odd man out. Okay. Let's go up to 20. Oh, one of my favorite molecules, caffeine. See what you can do with this guy. Okay, I got a 2 D's and a C. I'm going with D. Let's talk about Y, okay? So this is KB. Remember, pH is driven off of Ka, right? So Ka, if I take this guy and subtract 4 from 14, what do I have? 10, okay? So, but that 4 is going to drive it up into the 11 or 12 range. So because of that, my pH is going to be 11 to 12. Because remember, if we take this guy, the KB, and do the Ka and figure out the Ka, that's going to tell us where we're at.
Would another valid reason for this problem, at least, be because it's a base and they didn't
Yeah.
say anything about adding an acid to it?
Yeah. Yep.
Because that's how I figured it out, at least.
Yep. So, I mean, it is a weak base, so it's going to fall into that range anyway. So, yeah, that's another way to do it without even doing any math. Yeah.
I was gonna say, like, if isn't it like the more like positive it is, like the higher the pH is gonna be, since it's a little bit, like, even though it's a weak acid, it's a little bit stronger because it's only, to the -4.
Yeah, but it's the -4, but this is KB. So its Ka value is going to be negative 10 to the negative, like 9, probably. I would guess 9 or 10. Alpha W divided by 1 to the -4. No, 4 to the -4. So the Ka value is 2.5 times 10 to the -11. So that would make its pH 11. All right, try 23. This one got me. I had to actually ask somebody about this one. Okay, so I thought it would be C. Honestly, guys, like I couldn't figure this out. I had to ask one of those expert people on AP on the Facebook group, and he talked to me about it, and he said, no, it's D. It has to do with the electrodomains. Let me pull up his little explanation here, okay? This guy knows what he's talking about. I thought it was those lone pairs of electrons, so maybe I've done a bad job of showing y'all how to do this stuff. I apologize if I have.
Well, wouldn't it be the positive end? Because the oxygens have way more, if it's a bed structure and the oxygens have way more electrons, wouldn't that be the negative end? Not the.
Yeah. So he said the negative end of the dipole is determined by the atom with the higher electronegativity value, not the location of the non-bonding pair of electrons. And the SO2 molecule, it is the oxygen end of the molecule that's negative end of the molecular dipole, because oxygen is more electronegative than sulfur. So he's saying that this end is negative and this end is the positive end. And this end is the positive end and this end is the negative end, which I've always kind of thought on this one to be the case. But here I hadn't really thought about it, you know? So yeah, this is the negative end. So both of these, the oxygen's the negative end on both of these, the lone pair is irrelevant. And this one then ends up being, they're different because the sulfur has those more electron domains. It's got 1, 2, 3, 4, whereas this one only has 2 electron domains. It also has more electrons here around it versus this guy. So I don't know that I haven't led you astray on this one. And I feel kind of bad about it because, like, I think oftentimes I'm like, oh, I got this stuff. I got it this year. I know and then a question like this kicks me and I'm just like, oh. Like everything else on this whole 60 question test, I was like, oh yeah, I got that one wrong, but I see why I did it. This one I did not understand. So I felt kind of bad that that was the case.
I think it makes sense.
Good. All right, as long as it does on the test for you. It does now, but I didn't think that way. That's not the way I was thinking. All right, see how you do on 24 here. So when I've taught you something wrong or I've led you astray, I feel kind of guilty about it. Is that head thumper? How you doing on it?
I'm eliminating answers.
Okay. Okay, I got 1 vote for A, I got 1 vote for D, and I got 1 vote for B.
I'm going to be the exact opposite. I'm going to go for C.
Okay. All right. So let's talk about this. Is step 1 unimolecular? How many molecules would I have going on here?
2.
2. So we're going to get rid of A because that's not valid. It's not unimolecular. It's bimolecular. So A's out. Wah, wah, wah. Increasing the concentration will decrease the rate. So you're telling me that if I go out in the hallway during the middle of passing time, I'm less likely to hit somebody than if I go out there right now. So B's out. Because increasing concentration is going to increase the rate of reaction. What about the temperature? If I increase temperature, how does that, what effect does that have on the rate constant? It's going to change it. Now, this one you might have kicked out because you're like, well, it's the slow step that determines it. That's true, but remember when your slow step is the second step, you have to sub in what that is equal to. So I have to go back up here. I have to see, oh, this is an intermediate. I have to bring this guy down as part of my rate law. So my rate law is actually this and this. No. Back the train up. Back that train up. This. Okay? And remember, this guy gets raised to his stoichiometric coefficient, and this guy is here. Okay? Remember, we have to sub that guy in?
Now I do.
I know, that's why we do these review sessions. All right, we have a beautiful diagram of bromine and iodine. Are these your new answers, or have you put, or are those your old ones? Okay. Ah, very good. Everybody got this one right. Excellent. Yes, I2 molecules have electron clouds that are more polarizable than bromine. Remember, this was one of the ones that I used as an example to say, hey, this guy is a liquid at room temperature. This guy is a solid at room temperature because this guy has a lot more electrons. They're more polarizable, so those IMFs are higher. Higher IMFs equal the fact that we're going to have higher London dispersion forces. Good? Okay. Let's go on to 26. Very good, guys. Good job on that one. This one is a little bit of maths, as they say in England, maths. right, everybody pick C. Let's talk about why that's not the answer. Here we've got 4 things and we have a 2 ATM, right? Now, does it matter that this is argon, neon, and helium? No, it's irrelevant. It could be anything, any kind of gas at all. It doesn't really matter, okay? Because remember, the identity of the gas is irrelevant when we're talking about these things. All right, so this has 4 particles and it's at 2 ATM. How many particles? This is at 2 particles, so how many ATM would this guy have? 1 ATM. This guy has 12 particles, so what ATM would he be at? 6. All right, so now we're going to take 2 and 1 is what? 3 plus 6 is 9 ATM. But what do we do here? We changed the volume, we increased it. So it's going to be 4.5 ATM. So B is going to be your correct answer here. Be careful, they're sneaky. I'm telling you, they are sneaky. All right, see how you do on this guy. They'll get you. Get you.
I just watched this in the video last night.
When I think about this, I always think about magnets and where I would have to input work in to make it work, and then where, you know, if you just put them there, it would just poof. So that's what I think about. And if you input work, that's endothermic. If you don't have to put any work in, then it's exothermic. It's going to give heat off. All right, we have 1 person with the correct answer. Good job, Miss Emma. Okay, so step 1, I'm having to take this salt crystal and I'm having to pull apart those particles. So I'm putting energy in to pull those things apart. Step 2, I'm taking my water molecules and I'm pulling them apart to make room for that stuff. Step 3, then the crystals go in there and they just go, boop, I'm attracted, and it doesn't take any energy. So 1 and 2 are endothermic. You have to put energy into breaking those bonds, okay? Bonds broken takes energy. Bonds formed is exothermic. That's going to release energy. So the answer is D.
I had it right.
Oh, you said, oh, I thought you had C. I'm sorry. All right, Austin was right. I'll look better next time, Austin. I'm sorry, honey.
This one I remember.
No math needed here. Just logic.
just realized the difference.
Austin, you gonna chime in? Nope. C. Everybody here got C. Good job.
Actually, last second I saw that AG and then
Yep.
wait.
Okay, so this is, they're mixing dilute AgNO3 with excess NaCl. So if it's excess NaCl, we know that we're going to have Na and Cl in the stuff. So here I don't have any Na. Here I don't have any Cl. So I'm getting rid of both of those right away. Then I need to figure out what else is going to be in here. Okay, so I know that I'm still going to have, I'm going to have sodium and I'm going to have chlorine. And so that's in both of these. But then I've got to figure out what else I'm going to have. Well, the Ag is going to go into the AgCl here. So we're going to form that. Since this was in excess, I'm not going to have, and then I had NO3. The NO3 is soluble. So we know we're going to have NO3. So that's still here. But we wouldn't end up having any Ag because that would have been used up. It would have gone to completion. Okay. So because of that, significant concentrations, yeah. Because of that, here we don't have any Ag. All of it's in here. So C is the one that we would want to pick. Good job. All right. 29. Austin, is this your answer to 29? Okay. All right. Eric, is that your answer?
Mm-hmm.
Okay. I don't know if you changed it or not. Yes, C is the correct answer. So all but one of you got that. Okay. So decrease in intermolecular attractions among the molecules in the flask would not be the correct answer. Increase in the strength of the same thing, not going to be it, but an increase in the number of molecules, that's going to increase the frequency of those collisions with the wall of the container. Remember, that's what pressure is. That's going to work there. Increasing the speed of the molecules that then collide with the walls with a greater force. That's not going to be it. All right, so let's see about number 30 here. Eric's going to make me cry. Everybody got C here? Okay. So increase reaction, the rate of the forward reaction increases until it becomes the same as the reverse reaction. That's not what equilibrium is. Okay. Remember, since the K, did they give us the Kp value here? I thought they did. No. So never mind. No, they were making us, yeah, never mind. So it's going to decrease, become a non-constant 0. So it's still going to have a rate. So stays constant before and after equilibrium. That's not going to happen. Not before equilibrium, just after. And then decreases to become 0. That's not going to happen either. So it's here increases until it becomes the same. Remember, the rate is not going to be the same backwards and forwards. A lot of times it'll be less one way or the other, and that's what your K value tells you. If that K value is greater than 1, then your products are favored, and the rate will be faster for the product formation than it would be for the reactant formation. If it's less than 1, then you're going to have more for the reactants. Okay? All right, so that's where I'm leaving off. See if you can get through the rest of this packet this evening. So questions 31 through 60. If you didn't do your homework last night, that's what I'd like you to try to work on, okay? All right, we got 1 minute left. I will see you tomorrow, Austin.
See you, Lippy.
Looks like I can get through about 15 questions.